Professor Paul is a fellow of the IEEE and other many international organizations. He has received many awards, including Prime Minister's Gold Medal. Professor Paul has served on the editorial board of approximately 30 internationally well-known scientific journals in computer science and engineering, including several IEEE transactions. So actually, there is a lot to say about sir. So I will short my introduction about sir, and I would like to request Professor Dr. Shankar Kumar Paul sir to start his session. Thank you. Sir, please.
Thank you very much. Good morning to everybody. Without losing much time, let me start my speech on granular mining in video analytics, shallow to deep learning. Before that, I say that I was very much interested in attending the conference at Noakhali in person. I tried very much to get the visa, but somehow I did not get it during the scheduled time that I wanted to have. So maybe next time, if I get opportunity, I would like to visit and talk to individual students and the faculty members. Now, granular mining in video analytics, if you look at my topic, it has got a concept of granular computing, data mining, video analytics. And the technology-wise, today, we will talk about deep learning, but before that, we need to have the conventional learning, and we call it shallow learning. Now, this will be my content. So I'll explain granular computing and its components in 2 to 3 slides. Then the significance of rough set theory, why it is so much significant for granulation or granules during the past decade. And then the generalized rough set and entropy, why it is significant for handling uncertainty in a video or any kind of data when the uncertainty is arising from granularity in the domain of discourse, as well as the uncertainty arising from overlapping concept or regions in the domain. And there are so many examples, but I'll consider only problem of object extraction and tagging under unsupervised mode, But similar technology you can apply for bioinformatics, social network analysis, so many. I will give you the reference, and this will be my novel contribution in this work, concept of granular program, concept of rough filter, and then the significance of granulated deep learning, why we need granulated deep learning, and with some examples for, again, tracking. And the concluding part, I will spend some more time to describe the challenging issues that will be, because today those researchers who have started working in granular mining or particular deep learning, they should not jump into the subject without knowing the theory and underlying backgrounds very much and in depth. So what is granulation? Granulation is basically replacing a fine-grained universe by a coarse-grained one, more in line with human perception. For example, when I'm delivering a talk to an audience, what I see that some old people sitting in the front side, some young people backside, the boys and girls in a cluster. So at least I can see that some clusters of girls, clusters of boys, cluster of old people. So this is what is called granule. That means I do not look.
Sir, can I interrupt you, sir? Would you like to share the slides? Sir, no slide shared.
Oh, no slides here?
Yes, sir. That's why I interrupted you. Sorry for that.
Sorry.
No, it's fine, sir. It's fine, sir. Thank you.
Now it's fine?
Not yet, sir.
It is okay.
Sir, coming up. Yes, now his slide is visible, sir.
Yes.
Thank you, sir.
Yes,
Thank you.
Yes. Sorry.
Thank you, sir.
Should we start from here or from the beginning?
I think
From the beginning. From the beginning, sir.
Okay, 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 no problem, no problem. So now this was my content. Now you can see, right?
yes, yes, sir. Yes, sir.
Now I will explain in 2 to 3 slides the basic components of granular computing. For example, granulation, granules, with some examples. And then I will explain why rough set theory has become so popular for granular computing during the past decade. Then I will explain in 1 or 2 slides what is the meaning or significance of generalized rough set and generalized entropy, which takes care of uncertainty arising from granularity in the domain of discourse and uncertainty arising from overlapping concept. I do not consider uncertainty taking care of the probability of occurrence of an event. So only uncertainty arising from granularity, uncertainty arising from overlapping concept, overlapping regions, and so on. And I will explain as an example the problem of object extraction and tracking in unsupervised mode. That you do not have any idea about the data. Now, this can be, concept can be used similarly to other domain like bioinformatics, social network analysis, formation of network, computation, so on. I will show you some of the references. And then the novel concept of granular flow graph, graph filter. And third part, and most important part, the why we need granulated deep learning. And the challenging issues means young generation researchers, they should not jump into the subject deep learning as because it has a very good future. Because if you want to love to contribute, then you have to know the background material, that we have to know pattern recognition, you have to know shallow learning, you have to know neural networks in depth, then you jump into the work. Otherwise, it will be again a disaster, what we have seen in 1980s when neural network came out very abruptly and we expected too much. Then after 7 to 10 years, it loses its interest. So what is granulation? Basically, it's a concept of natural clustering. For example, when I give a talk to an audience, what I see usually in a sketchy way, I see that some old people sitting in the front side, some young boys and girls in the back side, usually girls are clustered together and so on. So I can see at a glance that some clusters of young boys, young girls, old people. So these are called granules. Similarly, when I look at a scene, what I see that some sky, I see the vegetation, I see some street or river and so on. So these are called granules. So that means I do not look particularly into pixel by pixel. I do not look into it individually in a gathering. So it is a process like self-organization, self-production, morphogenesis, Darwinian evolution, which are abstracted from natural phenomena. So granulation is also a phenomenon which is abstracted from natural phenomena. And these clusters and segments thus we have generated as called granules. And therefore, it is a process of formation and representation of granules. This is very interesting. So this formation of granules, this is a challenging area, and representation of granules, keeping all information of the data or scene or the object you are just dealing with. Now, concept of granules, for example, it's a mathematically, we can say it is a clump of indiscernible entities. That means indistinguishable entities, indistinguishable in terms of some property like similarity, proximity, functionality, and so on, depending whatever you like, how do you define the indiscernibility with respect to some given attributes. If you increase the number of attributes, then this indiscernibility entities will change, the number of granules will also change. Example, when we talk about age, we talk about very young boy, young girl, not so old, etc. When we drive a car, what do we say? Slightly left, slightly right, sharp right, etc. So these are all granules. We do not say that how old in terms of age or in terms of angle. So in a school, when it's called school, we see each class or section. And there, in an image, you can see that there are 6 consecutive grade levels. You cannot discriminate with your naked eye. This is what is called Weber's law. So therefore, 1 to 6, 2 to 7, 3 to 8, this I can call also a granule. Now, if you look at this, here the granules boundaries are distinct, crisp. Every class has no intersection with another class. Here also, but here you see the boundaries are fuzzy, slightly left, slightly sharp right, very young, not so old. So granules could be fuzzy, granules could be crisp. That means depending on that, you have to pay more. So granular computing in one slide is an information processing paradigm that works with the process of information granulation or abstraction. And where the computation is performed in information granules, not the data points. That's most important. That means I extract some information, I call it information granule, or if I extract some cluster, I call it a granule. Then I perform the following information based on those information. That means I perform the operation based on some compressed information. And since I am playing with the compressed information, so there is a possibility of having computational gain. And therefore, we can use it for mining large data sets. That was our philosophy behind when we started working 10 years back, more than that it has a significant application to big data, large data. So in summary, it is a nature-inspired information processing paradigm where the basic elements are called granules. Granules are collection of indistinguishable objects drawn together in terms of some properties like similarity, functionality, physicality, proximity. For example, in genome data, we go by functionality. In our pattern recognition problem, we go by similarity. In our image processing problem, we go by physical proximity, and so on. And these granules, where do they come? They evolve in the process of abstraction and derivation of knowledge from data. So please keep these 3 in mind for my following parts of the talk. So now, given a granulated domain, that is set of clusters. In a school, set of sections. This is my granulated domain. Now I define a set over this, some concept, and approximate this set in terms of those granules from lower side and upper side. I will explain with a diagram. And this gives rise the basic concept of rough set in 1982. Professor Paula from Poland, land of mathematics. He was an applied mathematician. He has passed away many years back, about 7 to 8 years back. What is this rough set? So this is my information system. This is a granulated domain, I can call it, just like sections in a school. That means all sections may not be equal. And I consider Y granule because X cannot be discriminated for another in terms of X and Y. If I increase another dimension Z, then the granular side may be changed. So over this granulated domain, I define a set, crisp set. Now I ask you, how do you characterize this set in terms of granules? I can see there is one kind of yellow set of granules which definitely belong to this set. Another could be this orange, which includes these yellow granules. That could be also set where some of the granules definitely belong and some of them possibly belong. So this is these granules marked by yellow boundary is called lower approximation of this grid set. And these orange granules which includes the yellow granules, is called upper approximation of this green set. That will say crisp set defined over a granulated domain can be approximated by lower approximation and upper approximation. That means all granules definitely belonging to X, and all granules definitely belonging as well as possibly belonging. And when you take upper minus lower, you get the boundary granules. That means they possibly belong. And when upper equal to lower, we call it exact set or be definable. Otherwise, it is roughly definable. That means inexactness in the set is arising because of the granularity in the domain. For example, in an image, when you have pixel-wise work, I call it a granule. Its pixel can be considered as a granule. Similarly, if I partition it into in terms of homogeneous color or homogeneous intensity values, I call it another granule. Therefore, but this granule, when I say that what are the object regions, that is what I can say that this definition, this problem is arising because we have discretized our image into X and Y axis. If I would not have been discretization the image, then there would not be any kind of ambiguity because of the just roughness, rough set. So rough sets are basically crisp set with rough description. If you need any further example, you ask me at the latter part, because otherwise I won't be able to complete. This is an old topic, but unless it is clear, you will not be understood. So you just keep this to mind: lower approximation, upper approximation. This can be explained in a nice way. There are many examples. So if it is not clear at the end, you ask me. But for the time being, keep in mind, lower approximation means definitely belonging, and upper approximation means definitely as well as possibly belonging. And upper minus lower means possibly belonging. And those possibly belongings create problem in decision-making problem. So rough set are basically crisp set, though the name is rough, but basically it's a crisp description, but with rough description. And this rough description, the vague description of the set X in the universe in terms of lower and upper, that signifies the incompleteness of knowledge about the U. Incompleteness of knowledge. So when I use rough set theoretic approach in terms of lower and upper, my objective would be to reduce this incompleteness of minimize this incompleteness of news. So minimize incompleteness to make a decision. So when I was working at NASA Johnson Space Center for 2.5 years, 1994, then we see that I was listening to this rough set theory talk delivered by East European scientists. That time I had little information about image processing, my experience of pattern recognition, my experience of just fuzzy set theory. So when I hear this talk, I can see that uncertainty handling is one of the criteria in using lower and upper approximation, because that talks about definite possible concept, and granular computing using information granules. So the two important characteristics. This can be used for any kind of data science problems. Now I will explain what is the meaning of this information granule and upper approximation in the sense of machine learning. So suppose this is a granulated domain, this is a cluster. So I can know that if you have the little ABC knowledge of pattern recognition or clustering, so every cluster has got its code region, that means for which you do not have any doubt about their belonging. And those regions are always centered around the centroid point. And there is some region as marked by author will be always on the boundary. So I can call this inner portion as lower approximation and shaded region as upper minus lower, and totally together is a boundary. And I can compute the cardinality of the lower, cardinality of upper, just simply counting, and I can define roughness equal to 1 minus cardinality of lower divided by cardinality of upper. If lower cardinality of lower divided by upper is equal to 1, then roughness is 0. And this will be 1 only when there is no granularity. Now you see that in real life, this was the definition given by Professor Paula. But now we see that in real life problem, this granule and the set, both or individually, could be fuzzy. For example, when you work on a gray tone image processing problem, since it is you are working on a gray image, where the variation intensity is sinusoidal. So when you say that where is my background, boundary between two regions, you need to have some kind of uncertainty because boundary cannot be crisply defined. Therefore, the concept of set would be fuzzy. Similarly, when you work in image processing, if you work with 3x3 window, then 3x3 window moving, there are many operations where to move this 3x3 window, just like in deep learning also. So this 3x3 window could be discrete or could be overlapping. That means my set could be overlapping or crisp, set could be fuzzy or crisp. Now, if one of them becomes fuzzy, then the lower approximation becomes fuzzy, out approximation becomes fuzzy. And fuzzy sets are nothing but membership functions. Therefore, lower approximation is to be represented by membership function. Upper approximation also needs to be approximated by membership function. And you can compute the cardinality of the membership function just by taking the values of those membership values. And we can define accordingly in real life problem, generalized rough set, where lower and upper approximation regions could be fuzzy, characterized by membership function. So keep in mind, if one of them is fuzzy, the lower and upper becomes fuzzy. And this is the uncertainty modeling measure or index, where it takes care of the uncertainty due to overlapping, uncertainty due to granularity, not uncertainty because of the probability of occurrence of an element. So it's called generalized rough entropy. Now let's consider tracking problem. So I'm considering tracking in uncertain situation and unsupervised tracking. There could be many types. First, easiest way is that you segment in every frame. It's a video frame you must have working. It's a sequence of frames. So one simple way that you every frame you segment and then you put the segment in an array, you got the tracking. Second one is the use classification or estimation. So I will here show you two methods, one based on classification and one method of estimation. So I will be using granules which are of arbitrary shape, that means which is natural. That when you look at a scene, if there's a vegetation, you got a natural shape, which is arbitrary shape, river, house, anything. And tracking in ambiguous situation, granular program, granulated deep plan. These are the constants. So what I will show? So I use a kinetic data sets which has got RGB depth. I use the concept of three-dimensional spatio-temporal because video has temporal information, because between frames we need to have some extraction of information which is called temporal. Similarly, you use two-dimensional spatio color, one-dimensional color, and this will be extracted by region growing. That you take a pixel, you find the similarity in terms of intensity value, then if the intensity similarity is less than some threshold, you connect it. So that's how you grow it. This is a very typical algorithm, standard algorithm in the case of clustering or our segmentation. Clustering is one form of, segmentation is one form of clustering. So granules obtained from lower approximation, I will extract. Why a lower approximation? In that case, this is definitely belonging. So instead of background model, for which the literature very rich, I will go by the object model. That is, I will extract only lower approximation and I play with the lower approximation. And then I will use granules, not the pixels, for object background partition. So I make the decision making in rule based in granular level, not in the pixel level. So I forget pixel. Then I will make automatic updation of the rule base with flow graph. That means I make it more intelligent. and deals with ambiguous situation like overlapping objects, newly appeared object. That means you are tracking some object, suddenly another object appears. Multiple object, different direction, speed. Now, what is the modeling? Let's consider what is lower approximation of object model in a video. Suppose this lady is working exercise at FT. FT -1, this was a position. So I take the temporal information, difference, absolute difference. I get this one. That means this is a moving portion. Because static regions, they get subtracted. So this is the moving region. Similarly, another previous T2, I get this moving region. F3, I get this. If we go further, it will be more, but it will be expensive. So let's consider 3 previous plane. So among those, these are all different moving parts only. So I take the lower approximate union and intersection. If I take union of those 3, I get this. If I get intersection, I get this. That means this is the minimum moving object which will be present in all these 4 video frames. So I call it lower approximation. And here the pixel intensity, they will give me the code information, and this will be the maximum tolerance. This pixel intensity can be allowed to grow. So this could be my upper approximation. So I forget about upper, I just consider lower. So over the lower approximation, I now form granules, spatial color. That means I take this hit point, I draw one. So granules could be overlapping or one. Then one side, so this is centered point of this granule, this is centroid point of granules, and so on. So after we get the centroid point from granule, I go back. This is my centroid point. This is called 2-dimensional spatial color granule because I have used spatial information and the color information. Then I go by the depth information sequence. I get this another granule. So I call it 1-dimensional granule. So these together constitute what is called 3-dimensional spatio-temporal granule. Similarly, I get this. So it's a granules of different sizes. And from this information, I go back to FT domain. So I collect the RGB. And temporal I got only. I go to the depth domain. I collect the depth information corresponding to this pixel region. So I store those regions. So therefore, then I make a rule base in terms of range with respect to RGB, with respect to temporal domain, with respect to depth domain. And I see that these are my experience based on. Say, this is a object ideal if do not belong to not belonging, partial belonging, complete belonging, and so on. Complete belonging means it's a complex because these are all set. These are all set. So complete belonging, partial belonging, overlapping belonging, not belonging. So if granules do not belong to any of this, I call it background. If they belong to everybody, it's called object, typical. And there were 8, 9, they are ambiguous granules because same features, but different background object. So my target will be to see that these ambiguous rules do not fire much. So accordingly, I define a coverage factor, and if the coverage is high, then I say fine. If the coverage is low, I modify the granules, this rule base. But while I modify the granules, I do not modify all the features. That is my intelligent way of doing my granulated program. What do I do? So that tells me which feature of this granule is responsible for making error. Only I make this change, that error. So this lady is doing some exercise in the morning. Now you see that suddenly the right hand starts, but the tracker is not able to track it because it doesn't have this flow graph modification, adaptation. The same when I have flow graph based adaptation, see that means suddenly you are tracking a car and suddenly another car jumps. The system will be able to track that also. Similarly, here persons are moving in different direction, different speed. See, It's a reflection of the car. The shadow is not getting detected because we are using depth information. So depth information only takes care of the object, not the shadow. Here we use frames per second 15 and P, that means previous sample is 6 total. 1 plus 5. 6 plus 1, 7. Now I'm coming for complete overlapping or occlusion. Previously was two kinds of handling. Here I use concept of spatial color, same neighborhood granules. Whatever performance I do in the temporal domain, not in the spatial domain. I define neighborhood rough filter, borrowing the idea from electrical engineering, and that estimates location and color models of objects based on the previous frames. And this information, that means location and color, I use for computing the nature of variation in size, speed, direction of object, so as to locate objects in the next frame. So I get information from the first three, then I model the fourth one. And when I model the fourth one, I get the location in terms of, again, lower and upper. So I compute the entropy or roughness, and roughness is low, that means lower and upper is almost same. I call it track it. If the roughness is high, that means object is occluded. Then I use some measures called total tracking intrinsic entropy, which is quantifying the amount of occlusion. Then I take the upper minus lower region pixels and put it in the lower and put it in the upper and see where the roughness is minimum. So in electrical engineering sense, so I have video frames. So I take T minus 1, T minus 2, T minus 3 and 1. I take their union. And now say P changes between two successive conjugates. T to T minus 1, T minus 1, T minus 2, T minus 2, T minus 3 and so on. So I get for a P number of frames, here I get only one matrix and here I get P matrix. So I take the convolution 1 to P point convolution. And this convolution results me two output on the lower approximation, upper approximation. And this convolution operation is intersection and union. When I take the intersection, I get this. And when I take the union, and then I put a condition that these all pixels in the union operation, those who have non-empty intersection with the lower, I call it upper, because those are giving me the boundary pixels also. So 1 to P point, a convolution operator. For example, when we take the convolution, I get lower and upper. That is definitely belonging, possibly belonging. And from this one, I compute the variation in distance, variation in color, acceleration, and so on. And define signal to noise ratio of this filter, borrowing the idea from, resembling the idea from electrical engineering. This is my object, which I want to be more, and this is the background, which I want to be low. So I call it signal and I call background noise. So my objective will be low values of signal, 1. Low values of SNR. That means this should be low and this should be 1. Poor filter performance. And now if I see that result, it's a London Metro, one picture. It's a complete occlusion. So my poor performance means low signal to noise ratio. My objective needs to be make high signal to noise ratio. That means lower approximation should be more, and the boundary pixel coordinate should be less. So now you see that this is called prediction. The previous one was classification based, but here we are not classifying. We are just predicting, because we have 3 frames, 5 frames, 6 frames, and based on that information, we are predicting the location in the 7th frame. So in defined speed also, you see that one, nicely it is getting, even when it is occluded, complete occlusion. Similarly, is an laboratory. I'm showing because I will use it for deep learning cases.
Sir, can I interrupt you for a second, sir?
Do you need to interrupt me now or after the talk?
No, sir, I'm saying that we are like, if you can finish it in next 3 to 5 minutes, that would be great, sir. Because another session going to start, sir. If you don't mind, sir.
Then better actually just stop it here.
No, sir, you can go and conclude, sir, another 2-3 minutes, sir. That would be great. Then things will get better.
Now, what is then granulated deep learning? So granulated deep learning, because deep learning processes, because now you have got abundant of data. So deep learning process is time consuming and difficult to engineer. So that's why you like to have granulated deep learning. Now, what is the granulated deep learning? The purpose is to reduce computation time, improve performance. Okay, I know one slide I will take. Okay, so this is our basic model, which we published first 2020. So this is a typical CNN model, which is popular for handling image or video data. You know, must be one. Now, what we do, every time you take a pixel, you around a mask. So instead of that, we make a granule. So instead of scanning the entire image pixel by pixel, we jump it only one granule and we repeat the same for the same granule in the next frame. So therefore, if you have 32 by image with n granules, sliding the filter is done only n times instead of 3y. So your n is much less. Therefore, you gain in computation time. This is a result. You will take different kinds of granules, 3x3 simple window, granulated into rectangular granules, arbitrary shaped granules, and no granules. See that speed has increased. Tracking accuracy has decreased this way. Accuracy of detection has this way. If you use CPU time. Now you can see that instead of this, you can take this instead of one. So now let me just skip everything. Yeah. So evolution of the discipline. Pattern recognition started in 1960s, image processing 1970s, AI, machine learning, and expert system, it started in 1980s. Knowledge-based system started in 1990s. Then data mining started in 2000s. Big data starting in 2010. Now we call about data-driven science. So new approaches for different tasks, accordingly different models. So new terms one, big hope. Thank you very much. Thank you. Thank you.
Sir, thank you. Sir, thank you so much. It was very much enlightening, and really from the audience side, being a session chair, I learned the very interesting things that our advanced machine learning, like a granules, can actually make things better. As granule-based deep learning can be the future. And thank you so much for your very timely presentation. Sir, if you allow me, I would like to take 1 or 2 questions, then we can actually conclude the session.
Sure.
Any question from the audience? No question from the audience? Sir, I have a question. So the question is, when we would like to use granule-based deep learning, do we need to have a more computational power, or what we have in our hand for the deep learning, that is sufficient?
Enough.
Okay.
Enough.
Sir, we have another question.
Sir, thank you for the presentation. So I'm not a computer scientist, I'm a biological scientist, and my concern is if it is possible to implement for biological science, like, the microscopy things, the electron microscope, they are using some of the object-based things. So is it possible to use
Yes, concept of granulation has been defined not for the deep learning. It is, as I mentioned before, it is for any kind of image data, any kind of data, whether it is low scale, medium scale, large scale, wherever you have ambiguity, wherever you have the concept of just granularity required in your algorithm. Granules means cluster of indistinguishable objects. Keep it in mind. So you play with the indistinguishable objects to reduce computation time, to get better uncertainty modeling. Now you are using it for advanced, how to do it for deep learning, because deep learning is very much expensive. Deep learning is very much difficult to engineer. So if I can use it and can reduce the computation time, maybe sacrificing little my accuracy. That's the objective. Yes, definitely.
Thank you, sir. Thank you. It's very enlightening. Sir, I would like to request you to, when you get the visa, come to NUST and give a workshop. Then these young researchers and scientists get benefit of this kind of in-depth talk. Thank you so much for your time,
actually,
sir. Now,
for that, I need a separate letter, because this letter will not allow. So maybe in the December, January, at your convenience, if you feel so, please just send me a letter. Then I will apply for a fresh visa. Okay.
Sir, university authority will contact you and make it happen. So
Okay.
now there is a opportunity to hand over a crest for you. As you are not here, one of the faculty member will actually take the crest on behalf of you and arrange to send you to your place.
Oh, thank you very much.
Sir, can you stop the slide share and show your video? Everyone want to see your face. And sir, you will be happy to know that now audience is full. Here you can see that more than 100 participants listening you talk.
Oh, very good.
Sir, everyone is excited. So we should have a clap for sir.
Thank you very much. Thank you. No, because you see, during pandemic, we gave several talks, but I don't enjoy. So now I have decided, if I go for in physical person, then and only then I give talk. But otherwise, without talking to our students, faculty members, I do not enjoy nowadays. Thank you. So should I close it or leave it?
Thank you, sir. Sir, we have a press handing session, and this session
Okay.
will be conducted by the session moderator and the session chair. Sir, the crest will be received by
Oh, Atiku is here. Okay. Thank you, Atiku.
Parna Sharkan ma'am, and the crest will be handed over by the Firuz Ahmed sir and Deepak sir. And also Shamsul Arifin sir is present here, sir. No, sir. Parna ma'am.
Thank you
Have
very
a
much.
round of applause for sir.
Thank you very much. Thank you. Should I leave now, Atiku? Huh?
1 minute, sir.
Yes, sir. Yes, sir. Thank you, sir.
1 minute.
Thank you very much.
তুমি মাঝখানে যাও এই যে তোলো আমরা যখন তোলো নেক্সট কে আরফিন ভাই না আসো আরে আমি গেস্ট কই না আমার তো দরকার না সেশন চেয়ার আমার কথা শুনেন না আরে ভাই আমি তো সেশন চেয়ার একজন মানুষ কবে সেশন চেয়ার একটা সাদা নাম বলছিলাম পরে আচ্ছা মামুন ভাই আর কি আছে না আমারটা ওনার
Thank you so much. You can close now, sir.
Sir, thank you so much from the University Authority. I am telling you that certainly you will get another letter and you will visit our university for the young generations, just to encourage our young generations. Okay,
Sure,
thank you,
sure.
sir. Thank you, sir. Salaam. Thank you. Bye.